So yeah, now we are continuing with the metamorphic rocks. And the metamorphic rocks are actually these metamorphic rocks for which the metamorphic facies diagram was originally constructed. Yes, you know by now the metamorphic facies diagram. And only to tell you, you should study the metamorphic facies diagram and all the minerals which are occurring in the different facies. Yeah? So when this metamorphic facies diagram was made by Escola in 1950, and he has constructed this for the metamorphic rocks. So because only a metamorphic green schist is green and only a metamorphic blue schist is blue, the green schist is green because of the mineral chloride, and the blue schist is blue because of the mineral glaucophan. You know this by now. So now we have here some pictures. So in these metamorphic rocks, they had always a mafic rock as a protolite. Yeah? That means the protolite of these metamorphic rocks has been igneous mafic rocks. And what is now an igneous mafic rock? That is, for example, a basalt. Yeah? Mafic means we have intermediate to undersaturated silica concentration. Yeah? That means you have then about a SiO2 concentration in your protolite ranging between, let us say, 45 and 52%. So in our first picture we have here a eclogite facies basaltic pillow lava. Yeah? So you saw during your field trips, especially on the ES106 field trips, we showed you pillow lavas, yeah? And on the coral trip you saw also pillow lavas. So and now you know that pillow lavas has been formed while you have eruption and this magma or mafic melt was cooled down very fast, and that is due to the contact of water, yeah? So that means that was intrusion at the ocean floor, for example. So and now we are taking our ocean floor and sending them into a subduction zone. We have done this in the past a lot of times, yeah? And now we are doing it again. So here we have the continental crust. Then we have here our subducting slab. Here we have the middle ocean ridge. Yeah? We have here the production of new basalt and new ultramafic rocks. Metamorphism of ultramafic rocks we have done yesterday again, yeah, because I was yesterday too late. And then I thought I will just repeat something, and then for those who left earlier or have not been in class yesterday, they can then watch the movie while I'm talking about the ultramafic rocks. So and here we have the seawater and here we have a ship. So that's always good to make a ship on it, because then everybody knows that we have here water, yeah? So if we would talk about some rocks here in the sky, then I would make an aeroplane. Yeah? So anyway, here on the top we have our oceanic crust. That means the basalt and the ocean floor, the basalt and the gabbros and the sheeted dye complex. So and then you know hydration, because I saw it just yesterday again. You had some questions because of the hydration of the basalt. Now we are hydrating the basalt, and the hydration of the basalt takes place along fractures and cracks, yeah? So they can be also perpendicular, yes, here to the surface. That means they are running in this direction. So in this cracks and fracture, hydration took place. Then we are sending the whole thing down here, yeah? And here the oceanic crust above as well. And then we are making from our pillow lava, maybe it's lying around here, and in the depth of about 30 kilometers, something like this. We are making now, due to the dehydration again of our hydrated material, we are making here now an eclogite, yeah? So, and you know these eclogites, you know now where the eclogites are sitting in the metamorphic facies diagram. These are these high pressure rocks. So, but here you can still see the shape from the pillow lava. I'm not sure if you can see the shape of the pillow lava, yeah? But then you just use your imagination, and then if you are watching 10 minutes of it and you are thinking you have to see now the shape of a pillow lava, then you will see it. So, but anyway, we have here the pillow core and here the pillow rim. So, and this pillow lava here is rich in the mineral glaucophan, and the glaucophan is this typical mineral which makes the bluish blue. And if you are running then or through your PT facies diagram, then you will see that you can produce from a blue schist, you can produce later on an eclogite. So that means we have here, when we are producing out of a blue schist an eclogite, we are dealing with a steep subduction. So the next picture shows us again an eclogite with the typical minerals in an eclogite. The rock-forming minerals of a typical metamorphic eclogite. These are two minerals, and that is the mineral ophrosite, that is a pyroxene, and it is the mineral garnet. So, and there is one mineral which never occurs in an eclogite, that is the mineral plagioclase. Yeah? So, an eclogite which contains a plagioclase is not an eclogite. And you must be aware of this, because that could be a question in the examination. So now we have the next picture. Here we have a pumpelite and a stilbite, and here what we have here, an opophyllite. So, and these minerals, the pumpelite, that is actually a very hydrous mineral, and if we are talking about very hydrous minerals, then we know that we are dealing with low-grade metamorphic conditions, and the pumpelite is indeed a mineral which occurs in a very low-grade metamorphic conditions, like under sub-green schist facies. Yes? If you are checking again your metamorphic facies diagram, then the sub-green schist facies is under sub-green schist facies conditions. We are dealing with very low pressure and temperature conditions. So that means such a pumpelite and stilbite, I think, is inside, yes. We are forming here at the middle ocean, or here at the ocean floor, due to hydration, yeah. So, and then we have here another picture, which contains CPX, OPX, plagioclase, CPX, garnet. So, and that is then, of course, also a very high-grade metamorphic rock, metamorphic rock, yeah, because we have here two pyroxenes inside, the CPX and the OPX, and there's only one rock type which contains both pyroxenes, and that is the granulite, yeah. So, and the granulite is formed at temperatures above 800 degrees Celsius, yeah. Also check for the examination all the pyroxenes. Yeah? Could be that there is a question about the chemical composition of the pyroxenes. Yeah? But I'm sure that you know this by now. I mean the chemical composition of the pyroxenes. So, and these are then all minerals occurring in the garnet, not the mineral and their compositions which occur in metamorphic rocks. So, and there we have, as a nesosilicate, we have the mineral garnet. Yeah? We are also aware of all the silicate structures. Yeah? The nesosilicate, the sorosilicate, the chain silicate, the double chain silicate, the sheet silicates, the tectosilicates. So in the garnet is a nesosilicate. You should remember this then in 3 or 4 weeks. And as the olivine is also a nesosilicate, but the olivine is not listed there because the olivine does not occur in metamorphic rocks. So then we have sorosilicates in metamorphic rocks. We have kyanite, suicide, epidot, pupillite, vesuvionite, lawsonite, chloritoite. So and then we have the pyroxenes, the chain silicates. And here in the metamorphic rocks, we are dealing, or we can find dioxide, jadite, hyperstein, that is a mixture between an andesitite and a ferrosilite. And here very important, the omphacite, and the omphacite is also a klein pyroxene, as I told you, but the omphacite occurs only in eclogites. So, and then we have the amphiboles. The amphiboles are the double chain silicate. We can find in metamorphic rocks the tremolite, the actinolite, glaucofen, barosi, Jaumatit, and the famous hornblende. So then we can find sheet silicates. You know this by now, that is the muscovite, for example. But under blue schist facies condition, you can also find the paragonite. So and then in amphibolite facies conditions, or even in granulites, you can find some phlogopites. These are then the 3 octahedral sheet silicates, whereas the muscovite is a d-octahedral sheet silicate. So then we can find the pectosilicates, that is the quartz, the anorthite, albite, analcite, and scapolite. You don't know by now what a scapolite is, and that is now also not important for you. So, and then we have the zeolites, and the zeolites are these minerals which occur under very low-grade metamorphic conditions like under subgreen schist facies conditions. And we can find some carbonates as well, like the calcite, the aragonite, and the dolomite. So, but now we need a proper projection for our metamorphic rocks. Yeah? You know by now, to describe the metaphylites, we use the AFM projection. To describe the mersolites, we use the CMS projection. To describe the harzburgites, we use the MSH projection. Yeah? So and now we have to think about what useful projection we can use to describe the metamorphic rocks. So what are the main elements of the rock-forming minerals in metamorphic rocks? That's the first question. So, and therefore we have, of course, due to the fact that we can find alumosilicates in metamorphic rocks, then at one corner we are putting the A, and the A we are putting for aluminium. So, and then we have here F. So there we can use then the iron end members, as well as the magnesium end members. That is due to the fact that all these iron-bearing minerals has then also a magnesium end member, yeah? And we have C for the calcite, for example the calcite, because calcite is a carbonate which occurs in metamorphic rocks, and a lot of calcium-bearing minerals occur also in metamorphic rocks. Therefore, we are using now the ACF projection for the metamorphic rocks. So, but we have also sodium and potassium-bearing minerals inside, and therefore we can construct a tetrahedron, and on the fourth corner we are putting then sodium or potassium. So, but if we are looking for a ternary system, then we are just using aluminium, calcium, and iron. Or you can instead use of the iron, you can use magnesium. Yeah? So, and then you can plot in your triangle all common minerals which occur in metamorphic rocks. Yeah? There we have here, for example, we have the garnet, the chlorite, the orthopyroxene, orthoamphibole, and tal. Then here on the negative side we have the biotite. That is because the biotite you are doing the projection out of this corner. So, and if you have a biotite, then it plots on the negative side. That is just a mathematical thing, but there you must, as an ES203 student, not take care of it. So then we have here, I mean, the length of the bar here that shows or give you an impression of the iron, magnesium, calcium exchange in the garnet. Yeah, if we are sitting here, then our garnet has a little bit more calcium inside, and here it is then the pure iron end member. So then we have here the amphiboles. They are plotting in this field, and that is if you are running from this direction into this direction, then our amphibole becomes more and more rich in aluminium. Yeah, you know that such an amphibole can make an Chalmers exchange, and then you are putting just more aluminium inside. And if we are talking about an aluminium-rich amphibole, then we are talking about an amphibole which was formed at higher pressures, and that is due to the fact if the pressure increases, then the volume of one unit cell will decrease, and the aluminium is a smaller atom compared to the magnesium, and then you are putting just some aluminium inside. So then we have, but you know this by now, we have done this. So then we have here the clinopyroxenes, yeah, that is then the mixture between diopside and Hedenbergite. If we are running more into this direction, then we are putting more aluminium inside. That means we are forming on this line towards to the aluminium end member or corner. We are forming then a more omphacite or an orchite. Yes, you know now the orchite from the excursion. Or you are forming just an chardiate. Yeah. So then we have on this side we have the grossular garnet. Yeah, that is the calcium end member. Then we have the anortite plagioclase. We have here the margarite. Margarite, you know this by now, that is a dioctaedral mica, and the dioctaedral mica, we have three end members. That is the paragonite, that is the sodium end member. Then we have the muscovite, that is the potassium end member, and then we have the calcium end member, and that is the margarite. And of course, it's plotted then on this side. So here we have then some staurolite. The staurolite you know by now also, because staurolite occurs also, or is a very common mineral in metaphylitic rocks. So, and then we have here on this corner, we have also the cordierite, the chloritoid and the spinel. We have heard also about the cordierite while we were talking about metaphylitic rocks, and the cordierite is a mineral which is formed under the high temperatures but low pressures. That means such a cordierite is then formed in a contact metamorphic event. So, and here we have now a nice comparison between metamorphic facies, metamorphic rocks, metamorphic rocks and metaphylitic rocks, yeah? So, I mean, you know by now that the main difference between the metamorphic and the metaphylitic rock is that the metamorphic rock has an igneous mafic rock as a precursor, which means a basalt or a gabbro, and the metaphylitic rock has a sediment as a precursor, yeah? So, but then we can just throw such a such a sediment and such a basalt, we can just throw them in a subduction zone, yeah, because here you have the trench, and the trench here is full with sediments, yeah. So, and here on the ocean floor you have also some sediments, and now you are sending just the whole baggage down, and then you will form a metamorphic rock and a metaphylitic rock. So, but the metamorphic rock has different minerals compared to those of the metaphylitic rocks, but some minerals are the same. So, and now we are sending them down at first through green schist facies condition, and then to amphibolite facies condition. So then that means the green schist we are making somewhere here, yeah? let us just choose some colors. So, because the green schist is green, and if we are talking about a subduction zone, amphibolite, and it is more bluish, so then we are forming here, maybe we are forming the green schist, and here we are forming the blue schist. So, but you can form the green schist also here due to metamorphism or at the middle ocean ridge, as well as the amphibolite. So, and then under green schist facies condition, we will find chloride as in the typical mineral in metamorphic rocks, and in the metapelitic rocks you will also find chloride. So, you will find plagioclase. So in the metamorphic rocks you will also find plagioclase. Yeah, but the plagioclase is then reacting away in the transition zone from the green schist to the amphibolite. So whereas in metapelitic rocks you can find the plagioclase through the whole green schist and through the whole amphibolite. You have just a chemical exchange in the composition of the plagioclase. That means if you are running to higher temperatures, then our plagioclase will become more and more rich in calcium. Yeah? So then in the transition zone we are forming then biotite also under green schist facies conditions. We have this also under in the metapelites. Then we are forming here in the amphibolite condition we are forming garnet. We are forming here as well garnet. So later on we are forming staurolite here, and the staurolite we have here also in the amphibolite, in the metapelite, and later on under higher temperatures we have here the sillimanite, and here we have the sillimanite as well. So, but what is different? Some of the minerals occurring only under very small PD or PD ranges, like the mineral chloride in the metamorphic rocks, whereas the chloride in the metapelitic rocks occurs only also under green schist facies conditions. So there is no difference. But in the metapelites we have muscovite over the whole PD range, and here in the metamorphic rocks we have muscovite only under less condition, in less concentrations. So then we have the biotite. Biotite occurs in the metapelitic rocks over the middle green schist facies conditions throughout the whole amphibolite facies conditions. And here if we are talking about the metamorphic rocks, we have biotite only. We have biotite only under upper green schist facies conditions in low concentrations. So the same for the albite. We have only the albite in the upper green schist facies and in the lower amphibolite facies, whereas albite occurs here in the metapelitic rocks over the whole PT range. Then here we have, for example, we have the oligoclase andesine, and the andesine, you know, these are more calcium-rich bearing plagioclases. Here we have the epidote. The epidote does not occur in metapelitic rocks, and we have here the amphiboles. And we have here the amphiboles. Amphiboles does also not occur in metapelitic rocks. So these are some of the main differences in the mineral composition or between the metamorphic rocks and in the metapelitic rocks. And if I would be you, then I would study this diagram for the examination. So here we have also another very useful and nice diagram, and that is that shows you the composition of all paragenesis throughout the PD space. So here, if we are running along here this PD path, then we are dealing with typical PD paths occurring in a subduction zone. That means low temperature, high pressure. If we are running through this PD path, then we are dealing with a PT path. Which occurs in a continent-continent collision zone, yeah? And if you are running along this PT path, then we have a PT path typical for contact metamorphic conditions. So, and then for here we have this triangle. That is a triangle which shows you the composition of the basalt, yeah? So, and I'm closing this now because I'm getting otherwise sick because of all this shit here. So, and that is then the basalt here with quartz in excess, yeah? If we are talking about a basalt with quartz in excess, then we are talking about a tolite, yeah? So there is also a basalt which is made up at the middle ocean ridge, but it is a basalt which contains some quartz inside. And if you are looking at your documents which I handed out very early at the beginning in the class, there I showed you the basalt tetrahedron, you remember? So, and there we had the quartz saturated basalt and the quartz undersaturated basalt and the intermediate basalt. So, a typical minerals in such a basalt, that is then plagioclase, clinopyroxene, orthopyroxene, yeah? So, and now we are taking this basalt. At first, we are hydrating our basalt, yeah? So, and that we are making just from here to there along fractures and cracks, yeah? There we are hydrating our basalt, and if we have put a lot of water on our basalt and also CO2, then we are making this out of our basalt. We have the mineral laumontite, we have dolomite, we have chlorite, and we have fenchite in excess. Fenchite, that is also a dioctahedral mica, and the dolomite, you know, that is a calcium, magnesium bearing carbonate, and you have the chloride. So there we have now our starting material when we have hydrated our basalt completely. Yeah? So, and now you can choose if you are going this way, or if you are going this way, or if you are going this way. So what you have in nature, a lot of passes between, yeah? These are just three representative passes, yeah? So if you are going this way, then we are running here in the subgreen schist, yeah? If you are checking your metamorphic facies diagram, we are running here into the subgreen schist. We are forming here, while we are running out of the subgreen schist into the blue schist. We are forming then here the actinolite, and the actinolite, you know, that is an amphibole. Then we have the mineral paragenesis in this rock between actinolite, chlorite, lawsonite, and fenchite. So now we are running here inside the blue schist. Our actinolite disappears, but we are forming then under blue schist facies conditions the mineral glaucophan, and the mineral glaucophan is also an amphibole, and this is the blue amphibole, and that is the reason why the blue schist is blue. That is because of the glaucophan, and the glaucophan, that is a sodium-bearing amphibole. So then we have still chlorite, and we have lawsonite, and we have now also epidote. So epidote, this is a greenish mineral, and it forms always bubbles. I mean roundish, they are roundish in shape. And we have fenchite plus paragonite in excess. So the paragonite, you know by now also, that is the sodium-bearing dioctahedral mica. Yeah? That is a mica which occurs under high pressure conditions. So and now we are running here along the path, we are running out of the blue schist into the eclogite. So and then we have here an eclogite containing of garnet, glaucophan, clinozoisite, and fenchite and paragonite in excess. So if you are running, or if you are continuing here, then we are running here into the eclogite. We are sitting now in the eclogite phases. That is in the transition zone between the eclogite and the blue schist. And here we have then the typical mineral paragenesis in an eclogite, that is the omphacite and the garnet. Yes, you can have also a little bit talc inside the glaucophan, but in an eclogite, the two typical minerals, that is the omphacite and the garnet. So these are the possible mineral assemblages if we are sending our hydrated piece of basalt down in the subduction zone. Yeah? That is the case like in the Andes. Yeah? So, but the next place where you can find this situation, there you can find blue schists, real blue schists and real eclogite. The next place here, that is in New Caledonia. So in New Caledonia, you can run around on your blue schist, and you can run from your blue schist into the eclogite. Yeah? So and we are just trying to reorganize the New Caledonia field trip. So maybe we can go there next year, yes. But having then all these field trips, we do not have any more time for having the class. So, but anyway, now we are running theoretically in a collision zone in the orogeny, like you have it in the Alps, yeah. So, or that would be also a nice excursion to go to the Alps, yeah, because there you can then run, and I have done this. Maybe I should check if I can find the pictures. You can run in the Alps from the green schist, you are running really on the green schist, into an amphibolite, and then you are running into the granulite, and then you are running also into the eclogite. Yeah? Wonderful. So, but anyway, we have here now our hydrated piece, hydrated and carbonatized piece of basalt. We are forming then here dolomite, chloride, pumpelite, yeah, the pumpelite and the phrenite. Pumpelite and phrenite, these are these typical water-bearing minerals under subphasous conditions. Then we are running here into the green schist, we are forming actinolite, chloride, epidote, nearly the same like here. With sphangite in excess, we are sitting here in the transition zone, or let us say in the upper green schist phases, we have epidote, actinolite, chloride, and we have now biotite, yeah, biotite. So if you have a biotite formed under green schist phases condition, and you are checking this biotite under the microscope, then this biotite is a very greenish microscope, because the biotite which is formed here under low temperatures, that is iron rich. Yeah, that is an iron rich biotite, and these biotites then are greenish in color. So then we are running here into the amphibolite phases condition. We have here the green schist amphibolite transition zone. We are forming then, of course, because when we are talking about amphibolites, then one mineral which occurs always in amphibolites, that is the amphibole. Yeah? Otherwise, we would not call them amphibolites. Yeah? So, then we are forming the first hornblende. We have the mineral paragenesis between hornblende, chloride, plagioclase, epidote, and biotite. So now we are sitting in the amphibolites, and we have now an amphibolite, we have hornblende, garnet, plagioclase plus biotite in excess, increasing then the temperature and the pressure. What happens? If we are increasing in an amphibolite the pressure and the temperature, then the dehydration reaction will take place. So, and that means our amphibole will become consumed, and then we are forming the first clinopyroxene. Yeah? Then we have clinopyroxene, hornblende, garnet, and biotite. And here the plagioclase. Yeah? So, and now we are running out of the amphibolite phases, and we are running inside the granulite phases. Then all our hornblende will disappear, and we are forming or we are getting the typical granulite-facious mineral assemblage that is CPX, garnet, and plagioclase. Yeah. So if I'm asking you in the examination, what is the typical granulite-facious mineral paragenist, then it's the CPX, the garnet, and the plagioclase. If we are dealing with a continent-continent collision zone, or with the orogeny, yeah, it must not always be the collision of whole continents. Let us just say an orogeny, yeah, a mountain land. So, but if we are dealing here with this high temperature, low pressure PT path, which is typical for contact aureoles, yes, then we are forming here, or we have in here a mineral assemblage between hornblende, chloride, plagioclase epidote. We are forming here the first CPX, that is CPX, hornblende, plagioclase, and silimanite. Yeah. Later on, we are forming at higher temperatures. We have two amphiboles inside in our metamorphic rocks. Yeah. We have the autoamphibole and the hornblende, and the hornblende is the clinoamphibole and the CPX. And here under granulite facies condition, you have then a 2-pyroxene granulite that contains CPX and OPX. So that means 2-pyroxene granulites, they are formed at lower pressures compared to those to the 1-pyroxene granulites, and the 1-pyroxene granulites, they are formed at higher pressure conditions. So, and of course, later on you can then form also an eclogite, yeah. If you are running like this, then we have anthracite, garnet, and kyanite. So here we have then another PT diagram. So and that is just a composition diagram. We have here the mole fraction, the blue lines here, the mole fraction of the plagioclase. So here we have a labradorite that is actually an igneous rock, and the labradorite has a certain calcium-sodium ratio of the inside the plagioclase, and here we have a 0.5, 0.6, 7, 8, 9. So and that means if you are running from here to here, then our plagioclase becomes from here to here always more rich in sodium. Yeah? Because the sodium concentration in the plagioclase is also an indicator for higher pressure conditions. Yeah? So that means we have here a plagioclase which has 50% sodium, 50% sodium and 50% calcium. Here we have 60% sodium, 70% sodium, 80% sodium, 90% sodium. So if we are looking here at this PT pass here, that is for a fast subduction, yeah, that is we have here, we are dealing with a subduction zone, and in this subduction zone we will have a plagioclase with a higher sodium concentration, yeah. So whereas if we are running here along this path, that is for the kyanite type collision zone, yeah, kyanite type collision zone, you know by now also, that is just the orogeny, then this plagioclase which is formed in such a scenario is more calcium rich, yeah. So and then you can measure the mineral chemical composition of your plagioclases and of the other minerals, and then you can calculate the pressure and the temperature conditions. Yeah? That is, I mean, I told you this by now a lot of times, that is always a question of the composition or of the temperature and pressure condition, and therefore minerals will have then a certain composition, and this you can measure, and then you can calculate these phase diagrams. And that is the thing what I'm actually doing the whole day. Next picture, that is also like such a mineral zoning. So, and that is the thing, you have here different zones. So, and this is the thing, therefore you don't need a microprobe. This is the thing which you can do in the field, yeah? You can just walk around, and you have always to watch on the ground, yeah, because the rocks are lying always on the ground. If you would study ornithology, then you would like always in the sky, because ornithology, that is the science of the birds, yeah? So therefore you have to watch always the sky, and you have to be careful that no bird is shitting on your head. Yeah? Because that's the way how birds seeing the world. Yeah? They are seeing the world always like this. You know this for those of you who are hunting or shooting, yeah, that is such a thing, yeah, such a plate. And if you are shooting here in the middle, then you are getting maybe a prize. And that is the same for the birds, because they are watching you like this. So anyway, we are coming now back to our rocks. Yeah, here is the coming tonight. Don't forget the coming tonight. Yeah, coming tonight is very important for your barrel light. Yeah. So, and then you can walk around. Yeah, you can walk around. And I mean, these guys you can identify very easily because it's forming always very wide needles. Yeah, you can walk around, you can sample them, put the GPS in your field book. Yeah, in the real field book. Yeah, because if you are using loose paperworks, then you can go every few years there again, because you can't remember what you have written in, because the loose paperwork is lost or it came in contact with water. And you cannot see anymore any things what you have drawn. So, and then you can just classify the different areas where you are walking around in zones, yeah? So, of course, in zone 4, you have find the minerals which are formed under higher pressure and temperature condition. And here in zone number 5, you have then the diopside and you have the garnet, yeah? And if you have the diopside and you have the garnet, then you are sitting probably in a granulite, yeah? So, and these are different methods how you can make this your drawings, yeah? You can just make the mineral zonation that are, say, sub-green schist, green schist, amphibolites, upper amphibolite, and granulite, yeah? Something like this, yeah? So yes. So and here this also, I mean, that was made from Mr. Secchi in 1969. Yeah, most of yours have not been here in 1969. Yeah, but at least I was 1 year old, and I remember him very well. So and he made this in the Tanzawa Mountains in central Japan. Yeah? In central Japan or Japan anyway, you have to be always very fast as a geologist, yeah? Because they have a lot of earthquakes and a lot of volcanic eruptions. And last time they had a huge tsunami, and then you don't know if you can find these rock units anymore. Yeah? So, and here, what has he done here? That is from Mr. Emerson, yeah? That was in 1995, yeah? 1995, you guys were around, maybe you can remember it. That was done in the geothermal field of Nesjavellir in Iceland. You know, Iceland is sitting on the middle ocean ridge, it's very hot there. I mean, from the ground, from the atmosphere, it's not that hot because then it's more than Arctic. So and here he did also some mineral zoning, but depending on the depth, yeah. So and these were the hydrothermal mineral stabilities. So in such hydrothermal mineral stabilities, we can also study here and we can study them in Vanuatu, yeah. So because there we have also hydrothermal field that leads all the hot springs, yeah. And then you can sampling the water, then you can measure all the elements in the water, and then you can recalculate the rock units below with which the water was in contact, yeah. There one can do a lot of things. So now we have here this diagram from Mr. Zhou and Louis. This sounds always also very Chinese, but it was made here. The map is from Canada, that is from Vancouver Island in British Columbia. Yeah. So here we have a granitic intrusion. Then around your granite you have formed amphiboles. So and then more far away your fluid has cooled down. Then you are forming breaches. And then you are running here into the phrenite-tumbelite phases. That is then under low metamorphic condition. So that is then a contact aureole, yeah, because you have a granitic intrusion. The fluid which has been released from the granite was not or did not exceed temperatures of 750 degrees Celsius. Because if it would be more hot, yeah, let us say 900 degrees Celsius, then you would form a ring of granulites around, yeah. So at 750 degrees and 750 degrees that fits, because 750 degrees that is a typical temperature for a granitic intrusion, yeah. So then the fluid becomes released. So and then you are forming from your surrounding rock units here an amphibolite. And the precursor of these amphibolites and breaches, that was then the basalt orogenic, yeah? Because if it would be sediments, then you would form metapilites and not metamorphic rocks. So that was it for today. Not that early.
For the cutting of rocks.
Yes, I know.
11?
Yes, 11, that's fine.